Dear all, I am Dr. D. Malati, Associate Professor, EC Department, HR University, Warangal. Today I am going to present you about the EEG signal acquisition and processing. So we are going to simulate the Python program, and it is going to be simulated using Google Colab platform. I am simulating. Let me get the output and then line by line I will explain. Yes, EEG signal simulation, filtering and analysis. So first one we have to import the library functions. So import numpy as np. Numpy, it is in Python. So the library functions are imported. And then import matplotlib.pyplot as PLT. So wherever we find PLT, it indicates that plot. That is used to plot the graph. Output in the shape of graph or box plots or bar graph or histogram. So these are all the output waveforms which will be visible. And then import matplotlib.pyplot as plot. Okay. Now from scipy.signal import butter, comma, filter. So the signal modules. So from this IP library will be imported, and the signal functions are there are several signal functions, but in this program we are using only butter, comma, filter. So butter means butter was a filter type, and filter it is used to filter the signal. So finally we will get the signal without any phase distortion. Smooth clear signal we will get. First part is simulation parameters. Let us assign fs is equal to 250, that is sampling frequency in hertz. Number of samples per second is equal to 250. T is equal to np dot arrange open bracket 0 comma 10 comma 1 by fs. So it is a 10-second duration. That is in the time axis, that is in x-axis, starting from 0 and the measurement ends at 10. And this duration is divided into how many parts? It is equal to 1 by 250. So this 10 by this 10 part will be divided by the 250 parts. 10 by 250. So 0 up to 10 it will be divided into uniform time intervals. So actually what is the value? Step size is equal to 1 by 20 I told you. So total samples 250 into 10, 2500 samples. So 0 to 10 seconds will be divided into 2500 samples. Next next one, create simulated EEG signal. So EEG consists of multiple frequency bands. It is delta, alpha, beta, theta also. So alpha is theta why we have not included. It is very much of low in magnitude, that is why we are not considering. And it is also caused in the abnormal only. That is why we are not taking that theta. So 4 components are present in EEG, but we consider only 3. So delta, it is equal to 50 into np sine 2 pi 2t. That means for delta value the frequency is 2 hertz. So frequency is the that angular frequency is converted into ordinary frequency. So omega equal to 2 pi f. 2 pi f is equal to 2. In the same way, alpha equal to 30. So this is the magnitude. And this is, for alpha it is 30. 30 sine 2 pi 10 into t. So 10 is the alpha frequency. Then beta 20 NP sine 2 into pi into 20t. So 20 is the frequency of beta waveform. This generates, so what is the meaning, theoretical meaning for this? This generates a waveform delta in 2 hertz. Waveform of delta 2 hertz, amplitude is 50 microvolt and it is obtained in the deep sleep brain state. So that is the history of delta wave. And then alpha, it is 10 hertz and 30 microvolt and it occurs in the relaxed brain state. Beta is 20 hertz, 20 microvolt and it occurs in active thinking of brain state. Then formula used. So we know A sin omega t, that is A amplitude omega is 2 pi f. So we know. Then clean underscore EEG is equal to delta plus alpha plus beta. So all three are the components of clean EEG. And this creates a realistic EEG signal containing multiple frequency components. Then add noise 50 hertz power line plus random noise. Why 50 hertz? So we are getting 230 volt AC 50 hertz from electricity board throughout India. So in our country the AC for AC power line frequency is 50 hertz. So it is assumed to be equal to power line interference with 50 hertz. And then noise is equal to 40 into NP sine 2 pi ft. F is equal to 50 plus 25 into NP random dot INDN length NENT. And what is the meaning? So already we know there are two types of noise added. Number one, power line interference. So this is a 50 hertz sinusoid and it is common due to the electrical noise. And then it is random noise. So in this random noise type, we are taking the category white Gaussian noise and it uses RANDN open bracket close bracket. It simulates muscle artifacts and background noise. So actually this noise occurs due to the muscle contraction and due to the breath. So while breathing, a small amount of sound will occur. So due to those incidents, random noise will occur. And then noisy underscore EEG, it is equal to clean underscore EEG plus noise. So total input signal for any processing is equal to clean EEG in addition to the noise, because noise already is getting added by itself, so that every processing steps will also be applied on the EEG noise one also. So not only on EEG but also on the noise also. Now the EEG signal is contaminated with the noise. Actually it is corrupted with the noise. Next one, a Butterworth band pass filter. Pass band is equal to 0.5 Hz to 40 Hz. Now what is the meaning of pass band? What is the meaning of pass band? band pass filter, it is the type of filter which is adapted from the Butterworth filter. So band pass filter, it will have two cutoff frequency. Number one, lower cutoff frequency and then upper cutoff frequency. So the frequency components below the lower cutoff frequency will not be allowed, they will be removed. And the frequency components above 40 Hz will be removed because the high frequency components are assumed to be equal to noise. That is why they are also removed. Then low cut is equal to 0.5. So 0.5 means lower cutoff frequency. And then higher cutoff frequency is 40. So order is equal to 4. So normally if it is 1 means nothing, no matter, and 2, 3 means higher order. So order is equal to 4 means still higher order filter. Steep filtering will happen. And then one more thing, if the order is more, it is higher order, computation will be complex. But there will be a sudden transition either from stop band to stop band, otherwise stop band to pass band to stop band. Anyway, the transition from one band to another band, it will be sharp. That means immediately it will transfer. Suppose if the transition is diluted, then the filtering process will become mistake. It will be not normal. So anyway, error will happen. Proper filtering will not happen. That is why immediately, if only two conditions, either stop or stop. So in between another condition, if it exists, then filtering will not become good. So next one, Nyquist is equal to half of the sampling frequency. This is the criteria which should be satisfied. And then low equal to low cut by Nyquist. High equal to high cut by Nyquist. So lower cut of frequency divided by, if Nyquist is equal to Fs by 2, then it will be normalized frequency. The whole term will become normalized. So cutoff frequency will become normalized. In the same way, for high is equal to high cut divided by Nyquist. So the higher cutoff frequency will become normalized. And then we have to generate the filter coefficients, then only filtering actions will be held on. So here B comma A is equal to butter, open bracket order. So order is equal to 4, comma low means low cut by Nyquist. Already the value was determined, comma high. So this high value is also determined, comma Butterworth filter type is here band pass filter which is adopted. So now next one. So once again, why this pass band is 0.5 to 40 Hertz? The reason is EEG frequency range lies between 0.5. So normally when compared to other ECG when compared to ECG or any other biomedical signal, EEG signal magnitude will be very less, because when you take ECG, you will place electrodes in the surface of the heart muscle along with the movement of the blood. But in case of EEG, the electrodes will be placed on the scalp, and in between there will be an insulation layer. That is why pure conduction will not happen. That is 100% conductivity will not happen. So the EEG amplitude will be of very small when compared to ECG or any other electromedical signal. That is why EEG signal range will be from 0.5 and 40 Hertz. and then it removes DC drift. So DC drift means when it is less than 0.5, that is removed, and power line noise is 50 hertz. And then nyquist is equal to 0.5 into Fs, that is Fs by 2, and it is equal to 250 by 2, 125 hertz. So in this way, we are generating the filter coefficients. Now filtered EEG is equal to filter open bracket B comma A. So these two are the filter coefficient, numerator B, denominator B, comma noisy underscore EEG. So butterworth filter is chosen because smooth frequency response we will get, and there is no ripple in the pass band filter. That is why butterworth filter is adopted, and under which band pass filter in this EEG case we are selecting. Next one, plot noisy versus filtered EEG. So here plot PLT dot FI figure open bracket figure size is equal to 12 comma 6. So what is 12 comma 6? 12 is the breadth of the graph and 6 is the height of the graph. So PLT dot plot, it is open bracket T comma noisy EEG comma label is equal to noisy EEG comma alpha equal to 0.6. And then PLT dot plot open bracket T comma filtered EEG label equal to filtered EEG line with equal to 2. Now what is the meaning? It shows the noise reduction. 50 Hertz interference removed. Signal becomes smoother, and then PLTX limited range in the x-axis. It is 0, 5. So starting from 0 and ending with 5. And then what is x lim? So it stands for x-axis limit. 0 starting value of x-axis and 5 ending value of x-axis. That's all. And then plot x label. Plot x label time in seconds. Then plot y label amplitude in microvolt. Then plot title noisy versus filtered EEG signal. So for this graph, the title is noisy versus filtered EEG signal. And then PLT dot legend legend. I know what is the meaning. It is used to display the legend box on a plot. So now, graph around the graph, box will be provided. So it will be the graph will be constricted into the graph. It will be located intact. That is why we are using the legend. And then PLT dot show. So it is showing the output graph, and then time domain analysis. So mean underscore val, it is equal to np dot mean filtered underscore EEG. So what is the meaning? Average amplitude. The average amplitude should be close to 0. It indicates baseline level. So it is actually it is the reference line of 0. And then variance underscore val, it is equal to np dot where filtered EEG. And now what is the meaning for this? It measures signal spread. Higher variance means higher brain activity. And then RMS underscore val, it is equal to np dot square root np dot mean filtered EEG power 2. And what is the meaning? It is RMS value. It gives RMS gives effective power of the signal, that is root mean square value, and this is the formula. So RMS is equal to 1 by square root of 1 by capital N sigma x square. So it is the mean value and it is the formula. So higher RMS means if the RMS value is higher, then automatically it indicates that the signal is stronger and neural and the oscillations are neural. So finally we will get stronger neural oscillations. And then time domain analysis of filtered EEG. So the value will be evaluated and then it is printed. So value is printed. Print mean, so mean value is printed. Print variance, so variance value is printed. Print RMS value is printed. Finally, plot filtered EEG time domain. So here, PLT dot figure, figure size is equal to 12, comma 4. So 12 is the breadth and 4 is the height. And then PLT dot plot, open bracket T, comma filtered EEG. And then plot X limit. So it is already stated that limited X axis value starting from 0 and ending with 0. And plot X label, the same thing only. And for this analysis also same. Time in second for x-axis. Y label, it is amplitude in microvolt. And the plot title for this diagram, graph, the title is given as filtered EEG signal time domain. Here time domain analysis of filtered EEG. So next one, plot show. So the plot is visible. So finally, what we will get? See the noisy versus filtered EEG signal. So the blue signal shows the noisy EEG. Red signal is the filtered EEG. So how they vary? So almost we will get the confused signal here, so that we need to get the filtering. So in this analysis, time domain analysis of filtered EEG, the mean value is 0.9. Actually, mean value is 1. So here 0.95 we are getting. Variance value 2156.5. Okay. Next RMS value calculated is, it is already effective value or root mean square value. So nearly half of the value we will get. That is why 46.5 we are getting. Almost it is equal to 47. And then filtered EEG, which is in time domain. How the signal looks. It is a time in second x-axis, and in amplitude, in y-axis amplitude in microvolt, the same signal, the combined signal only, but only thing, the spikes available in the signal will be removed. Signals will be removed. Noisy EEG and filtered EEG both will have spikes, and those spikes will be removed, and we are getting the smooth signal in time domain. So here the filtered signal is also shown along with the EEG signal for comparison. So here theta, only thing, theta waveform is not shown because it is actually appearing in the infant only. So it is not showing. We are not showing the theta waveform. And one more thing, this simulation parameter, in the simulation parameter, Fs is equal to 250. So we are getting 0 to 10. This 10 up to 10, the final value 10 part is divided by the 250. So 10 by 250, what is the value? That is the interval from the first value to second value or second value to, so in between two values what will be the difference? It will be decided by the 10 by fx, 10 by 250, that is 1 by 25. So 1 by 25 means 0.4. So 0, 0.4, 0.8, 1.2. In that manner it will be ending at 20. So these three are the components of the EEG signal. So delta, alpha, beta. So delta is a deep sleep state, alpha is a relaxed state, and beta is the active thinking. And theta we will not take considering here. So this is the realistic EEG signal, and what are the frequency for the respective components are also shown here. So noise compulsory, and already already I have told you that EEG signal is of very low in amplitude, because the conductivity of EEG will be very small. That is why we are taking the low amplitude, low frequency EEG signal. And one more thing, in case of ECG, the signal will be of so, to some extent the magnitude will be higher, because we are positioning the electrodes around the heart skin. So whenever the movement of blood occurs, ions will be attracted towards the positive electrode or repelled from the negative electrode, so that both will cause the conductivity, positive magnitude as well as negative magnitude we will get in the ECG signal. It will contribute to some amount of peak, I mean the amplitude level. But here the scalp, that is the cortex part, we are providing the electrode, and that too it is pasted only, not entirely conducting, and aluminum Ag and AgCl, silver and silver chloride, both the electrodes with the reference, they are reference electrodes and are kept in the scalp, so the brain scalp, and that is why in between it is acting as a semiconductor. Sorry, insulator. That is why full conductivity, that means 100% conductivity we will not get. So the EEG amplitude will be of very small in magnitude, and when we collect the EEG signal, it is not pure in all biomedical signals compulsory due to our body muscle movement and blood circulation, the noise will be introduced, and due to the erection of the diode, our electrodes also, the power line interference we cannot avoid. Actually, it is not higher amplitude level, high current, it will not occur. But due to the electrons and movement of the ions, a small amount of electrical signal will flow. So definitely the power line interference will occur. So as usual, the random noise will be taken, and overall, why we are introducing the RAND and LENT, full processes, and that means sampling definitely we are going to do. We are going to apply on the signal. Why we are applying sampling signal? We are using the digital signal. Analog signal will be converted into discrete valued signal. So this is the digital signal, and it will be filtered. So when you are applying sampling on EEG signal, the same thing will be applied on the noise also. So the noise will be taken in the equal space. So if it is the length of the noise is less than EEG signal or greater than EEG signal, then the processing will not be. Suppose if you take one cycle of EEG, Then noise, if it is less, the full sampling number of samples are 100 samples will be applied on the EEG signal. Noise sample will become reduced, so that the conversion from analog to digital and applying the filtering process will become erratic. That is why length of the noise will be equal as that of the EEG signal. That's all. Thank you.